Last lecture today, we are going to focus on the modeling of scalar flux. So first we'll talk about closure of Reynolds scalar flux, and then we'll go into the alias context and the closure of subgrid scalar flux. We have already talked about scalar flux a little bit in the previous lectures, but this lecture will primarily focus on the scalar flux closure, and you will need that if you are actually solving for energy equation or if you are solving for any mass fraction equation. So that is the reactive scalar transport equation, instantaneous sense. As we discussed several times, that upon using Fabry averaging and then carrying out the averaging procedure will give you this. Effectively, for this equation, you are solving for Fabry average scalar. This term is a closed term. Essentially, this term is often negligible in the context of RANS, so often this term is neglected. This term is unclosed, this term is unclosed. The closure of this was briefly discussed earlier, how to actually model the reaction rate. Today we are going to talk more about this. So this quantity is commonly referred to as the scalar flux and usually modeled like this. Most of the time, if you look at the commercial goods, that's what you are going to get. It's called gradient hypothesis. It's similar to Fourier's law of heat conduction. Right? It basically, this negative sign essentially ensures that you have a diffusion process which is going from the higher concentration region to the lower concentration region. The only difference is here, this diffusivity is the turbulent diffusivity, and it is dependent on flow properties. Okay? And we talked about the challenges involving the closure of this term because of the highly nonlinear dependence on temperature and species mass fractions. The same thing, the gradient hypothesis model is presented here. This is essentially your kinematic eddy viscosity. So just for the sake of to avoid any kind of and this is the turbulent Schmidt number, usually taken to be of the order of unit. Advantage is that we already know that under turbulence the mixing rate goes up. So effectively, once you put it in the governing equation here, effectively we'll get a term very similar to this one with an augmented diffusivity, which will represent higher rate of mixing or higher rate of diffusion. It has some extra advantages that if you have more diffusion in your code, it stabilizes the numerical aspects as well. Disadvantage is that it is based on the analogy of magnetic theory of gases, and same situation is not valid for turbulent flows, which we talked about a lot yesterday. Gradient hypothesis model does not remain valid under some situations. For example, let's say you have a fully developed channel flow. This is the streamwise direction, right? And you will perhaps consider that there is a heat transfer within the channel. if it is fully developed, what is going to be the del T del X? No? Sure? Okay. If I would not say temperature, let's say some kind of other species, because temperature is not necessarily equal to zero. If I actually have heat flux at the wall, temperature will keep on increasing. So using temperature is problematic in that sense. So, let's say some scalar that's equal to zero, right? This is not going to be zero necessarily. If you do a direct numerical simulation, that's not equal to zero. So if you put it in this model, it's not going to actually give you the non-zero value of this one. So, clear? Can anybody think of any reason why still you get away with it? Because think about the boundary layer theory. Essentially, this term, if you use for this quantity, the second derivative in the wall normal direction is much, much greater in comparison to second derivative in the stringwise direction. So even if you actually incur some error in evaluating this, it don't make any huge difference. So you get away with it, but it doesn't give you the light. And you will see later on, gradient hypothesis essentially is invalid. Sometimes buoyancy dominated flows in some reacting flows. Counter gradient transport is observed. We talked about counter gradient transport briefly yesterday. We'll come back to that in greater detail today. There are some attempts to actually address these deficiencies. These are generally called tensor diffusivity model, where essentially in this part where you had some kind of rho bar times diffusivity in the earlier slide, there are some dependence on the local Reynolds stresses. Okay, so depending upon the direction, diffusivity changes. That's why it's called tensor diffusivity model in general. These are two variants, but there are more attempts in this regard. They are more successful than the conventional gradient hypothesis model, but mostly under non-reacting scenario. They don't really work very well in the case of reacting flows. But how do they perform? If you look at the resolution is not great, but black line is DNS. The other predictions are K epsilon Lauder and Sharma, that's the low Reynolds number K epsilon model. K omega SST, we discussed, you can actually bring everything up to the wall with K omega SST. Standard K epsilon model, this one magenta circle. Okay. LRR is a Reynolds stress model, SST is a Reynolds stress model. And if you are considering in terms of the wall normal Reynolds closure, in the wall normal direction, they actually do a decent job. The gradient hypothesis model. Obviously, you can actually match things by changing this one, which is turbulent spectrum. But for this purpose, we have kept it to be one. Clear? So, for simple boundary layer problem like a channel flow, it's not bad. Now, again, let me go back to the reacting scenario now. We saw this thing yesterday already. If I am sampling along this line, so instantaneously, let's say my premix flame looks like this. If I average, my C tilde is good for a given value is going to be along this line. So if I am sampling along this line, most of the time I'm seeing either product or reactant. Sometimes when flame process, this part gives me this bit. But there are two peaks, right? At C equal to 0, at C equal to 1. This kind of PDF is referred to as bimodal PDF. Effectively, you have two delta functions. And these are the delta functions. This delta function represents this. This delta function represents alpha and beta are the weighting parameters. This part, essentially, whatever is sitting in the middle. Often, it is referred to as burning mode contribution. Why burning mode contribution? It's obvious. Because it is coming from this region where C is between 0 and 1. Concept is clear? As I mentioned yesterday, that this contribution is going to be negligible if flame is thin, and in other words, it actually boils down to the fact if Dampoler number is very, very high, that means chemical time scale is extremely small in comparison to the large eddy turnover time. That means when the chemistry is extremely fast. Because think about this one, when chemistry is fast, everything is actually over in a very small distance. So essentially, I can consider my flame like just a membrane which is separating reactants and products. If chemical time scale is large, chemical reaction will go on over a large breadth of space. That's the idea. Clear? Similarly, the joint PDF of velocity vector and reaction progress variable can be drawn like this. Effectively, you have one delta function again for C equal to 0, another delta function is equal to 1. But this is the PDF of velocity in pure reactants. This is the PDF of velocity in products. So they are conditional PDFs. Conditional on reactants, conditional on products. Clear? You have seen them yesterday briefly, but we are now going to use them extensively. The idea is clear, physically whatever is happening. Happy with that? Now, in real life, that is the idealization that you saw. If I consider, let's say C tilde 0.5 from direct numerical simulation data, Dampoler number decreases from case A to C. So case A has the highest Dampoler number, case B is medium, this one is low. You can see what happens. Does it look like a bimodal PDF? This one does to some extent. But this has considerable probability of finding values which is between C equal to 0 and C equal to 1. So the burning mode contribution cannot be completely neglected. Yesterday, if you remember, I told that if you have a bimodal PDF, variance of C becomes C tilde times 1 minus C tilde. So the extent of departure, just to link yesterday's lecture to today's lecture, that if the variance is smaller than C tilde times 1 minus C tilde, you firstly actually note that bimodality is not maintained. The extent of departure gives you the measure that how much departure has taken place with respect to a pure bimodal situation. Fine? Now, you know when you integrate the PDF, you get 1. So that gives you 1 alpha plus beta. This equal to 1. When you integrate the delta function, effectively that value basically comes in. So you get alpha, beta, this. Fine? For when Dam-Coulomb number is very large, I already told this contribution is inversely proportional to Dam-Coulomb number. So when Dam-Coulomb number is high, you can actually ignore that. Then alpha plus beta becomes 1. Happy? At this point, I have to consider a couple of things. If I am dealing with Bhowmik number, unity Lewis number, just to remind you, unity Lewis number means thermal diffusivity is same as mass diffusivity. So all the species are diffusing equally. There are no differential strengths between the diffusion process of scalars. Okay? So if you have unity Lewis number, Bhowmik number, and globally adiabatic situation, that means no heat loss. Under that circumstance, this reaction progress value becomes same as the non-dimensional temperature. So a non-dimensional temperature is defined like this. T0 is the unbound gas temperature, T is the adiabatic flame temperature, this is the instantaneous dimensional temperature, and T is non-dimensional temperature. Clear? Now, if I have constant pressure field, ideal gas law, if I invoke, P equal to rho R T is another form of ideal gas law. So if P is constant, then rho times T must be constant. Clear? That gives me this. And from there, I can actually get an expression for rho bar, mean density. Clear? So there are a couple of things I needed to do. T0 is the unbound gas temperature, rho 0 is the unbound gas density. Effectively, this one, T hat, I can write in terms of this equation. That yields this equation. As C is equal to T, I am replacing T tilde by C tilde. Clear? This part, up to this part, it is valid even for non-unity Lewis number condition. The Lewis number condition alongside low Mach number and adiabatic flame allows me to replace T tilde. Clear? As I mentioned, tau in this case is a heat release parameter defined like this. I sent the updated slides to Dr. Barman yesterday. In the updated slides, tau value, tau significance is explicitly mentioned with the updated slides yesterday, but now it is explicitly indicated. I already have got this expression. If I consider density is only a function of C, which is the case under all those assumptions, then I can put rho C, PDF, and integrate. And if I integrate using this function, I will get this. See, this part comes because of the unbound contribution, the delta function at C equal to 0. Density there is rho 0. Clear? This one comes from the delta function at the bound gas equal to 1, and at that point density is rho rho 0 divided by 1 plus tau. Clear? Now, I have two equations. This is one equation. If I ignore this contribution, this gives me one equation. Another equation was the normalization condition. And if I take them together, that gives me this. Clear? If I want to find out C bar, I just have to do this integration. At unburned gas, C value is 0, so there is no alpha contribution. There will be only beta contribution. In the burned gas, what is the value of C? 1. So that's why it's just beta plus this. If I ignore that contribution, effectively beta value I know. So you can clearly see this equation relates C bar with C tilde. Towards the beginning of the course, I already told that Reynolds average value and the Febvre average value, they are not the same. You can clearly see that. Okay? However, this is only valid for premix flame, this expression. It's not a general expression, but at least one can illustrate that for at least one flow configuration that they are not the same. They can be considerably different, actually. If you want to actually plot C bar as a function of C tilde using this formula, and tau value typically for hydrocarbon flame is 6.5 something. You will see, if you just do a plot in Excel, you will immediately find they are considerably different within the flame. Obviously, in the unburned gas, C bar is 0, C tilde is 0. In the fully burned gas, C tilde is equal to 1, C bar is also equal to 1. But within the flame, they are very different. If I do this for density weighted variance, you will get this contribution, because rho is rho 0 there. If you put C to be 0, then you will get this contribution. For the burned gas, C value is 1. So you will get 1 minus C tilde square. Density is rho 0 divided by 1 plus. And then if you put the values of alpha and beta, you see this. We talked about that yesterday. That's why the C tilde times 1 minus C tilde equal to variance came into picture. Clear? Similarly, if I consider Ui tilde, Febvre average velocity, that is given by this expression, where this one is the mean velocity conditional upon reactants, this one mean velocity conditional upon products. And using the same methodology, now I can actually write this expression, C, rho is kept as rho, Ui double prime is Ui minus Ui tilde by definition. From the Febvre decomposition follows. C double prime is C minus C tilde by definition. And then I've essentially talked having the joint PDF is a function of two independent quantities, C and U. That's what I'm doing. And if you actually carry out, you will end up with this expression. And how you actually get that, we will see during the tutorial. Okay? And that gives me this expression. Let's see the implication of that. In a laminar flame, I mentioned that briefly yesterday, just bringing the analogy of a normal shock. If you consider the mass conservation across a shock wave, it's a similar kind of thing. Here density is rho 0, unburned gas. Here the density is rho b, which is the burned gas density. This is say for steady laminar flame. Laminar flame is trying to move towards the reactants with a laminar burning velocity. If you are seeing a stationary flame in naked eye, that means the velocity essentially balancing the laminar burning velocity. That's why flame is not moving. Okay? So the fluid velocity coming from here is SL, laminar burning velocity. From the mass conservation, this is what you are going to get. If pressure remains constant, this density must be smaller than this. So this velocity is greater than the velocity in the reactant side. So difference of UI B minus UI R, that means conditional mean velocity in product minus conditional mean velocity of reactant is of the order of this tau times SL. This is a slight departure from this situation. Okay? Which way the gradient goes? So, if I consider this to be x direction, what will be del c tilde del x? Positive, right? According to gradient hypothesis, which way you will get whether scalar flux will be positive or negative according to gradient hypothesis. Just to recall, so if del c tilde del x is positive, what will happen to U1 double prime C double prime? Positive or negative? Negative, right? If I have this situation where UIP is greater than UIR, what type of value you are going to get? Negative or positive value? Positive value, right? So clearly, it is not following this behavior, isn't it? And that gives rise to counter gradient type of transfer. Yeah? Okay? With the idea? If I have a situation where U1R is greater than U1P, then what happens to this term? Positive or negative? Negative. A negative flux, does it follow this? Yes. So then you will get gradient type of transport for this kind of situation. So effectively, this term in the square bracket is known as the slip velocity, because it's the velocity difference between the product and the reactants. If the slip velocity is positive, then you get counter gradient transport. If the slip velocity is negative, you get gradient type of transport. What really happens, we have already found out, this is the typical velocity jump in a laminar flame. Okay? If your turbulence intensity is such, which is much smaller than tau SL, this velocity jump, you get counter gradient transport. If U prime turbulence effects dominates over this velocity jump because of chemical reaction, then you get gradient transport. Okay? So it's a matter of competition between the turbulence induced velocity fluctuation and the velocity jump induced by thermal expansion as a result of chemical heat release. Clear? More or less whatever I mentioned, that is summarized here. Generally, this slip velocity nowadays is modeled by this. The logic should be clear by now, because I already told it's a competition between tau SL, that's the velocity jump because of the thermal expansion as a result of chemical heat release, and this one. 2 alpha is a modeling parameter of the order of unity. Basically 2 alpha is of the order of unity, it's the modeling coefficient. So you can see it's direct competition between these two. If this one wins, you will get counter gradient. If this one wins, you will get gradient. Okay? And based on that, they came up with a non-dimensional number called Bray number, given by this. So if Bray number is much greater than 1, you get counter gradient transport. If Bray number is much smaller than 1, then you get gradient transport. I had the opportunity to actually closely interact with Ken and Bray, under whose name Bray number was proposed. He's a very modest person. He absolutely hated the idea of somebody calling this parameter as Bray number. He was very embarrassed about that. So every time I say Bray number, I almost see him cringing. That's what he used to do. But, okay, out of respect, I told Bray number, but to keep his preference, I also want to actually emphasize, ultimately it's a matter of competition, whether tau SL wins or U prime wins. Okay? Modeling of turbulent scalar flux. You have option of algebraic closure or transport equation based closure. It's basically the same logic that we talked about when we talked about the Reynolds stress closure. Okay? And the same methodology is also valid for both RANS and LES. But however, it is not really common for LES to actually go for transport equation based closure, because LES is already computationally expensive. You don't want to carry extra transport equations. But in principle, you can have, nobody is stopping you. So, I'll talk about the big direct numerical simulation data set. You can see this one has very high Ampuller number, much greater than 1. Charlotte's number was small. In case you don't remember, this Ampuller number is a large scale turbulent time scale to chemical time scale, that's the ratio. And this one, Charlotte's number, gives you the chemical time scale to the small scale turbulence time scale that we spoke about time scale. And Lewis number is also changed. S, A, B, and F have unity Lewis number. Lewis number C is Lewis number 0.34, this is 0.6, 0.8, and this one 1.2. Why Lewis number is important? I'm digressing a little bit, but please understand that from C to G, flame is seeing the same statistically similar turbulence in the unburned gas. But you can clearly see the flame looks very different. the extent of flame wrinkling increases with decreasing Lewis number. And this is happening because of the differential diffusion effects. It's because of the differential diffusion of heat and species. Just to give you an idea what really happens, if you have this kind of wrinkles which are convex towards the reactant, reactants diffuse faster into those zones in comparison to the rate of heat diffusion out of those zones. Now I have high reactant concentration, high temperature. What will happen to the chemical reaction? It will get augmented, right? They will propagate faster. Just the opposite thing happens. Reactants in this kind of zones which are concavely curved, they are diffusing away much faster in comparison to the diffusive heat flux focusing there. So now I am actually having a situation where reactant concentration is small, temperature is going out, the heat is going out, reactants will actually, the chemical reaction rate will slow down. So essentially, a combination of high reaction rate here, low reaction rate there, means you can actually have higher amount of wrinkling, higher extent of wrinkling. Okay? And this effect strengthens with decreasing Lewis number. Just the opposite thing happens in the case of Lewis number greater than 1. In the Lewis number greater than 1, where it is convex towards the reactants, heat is diffusing out faster than the reactants come in. So now I have a situation whereby I have low temperature, low chemical, low reactant concentration, reaction rate drops. It does not propagate that fast. So it has a stabilizing effect, whereas Lewis number less than 1 has a destabilizing effect. That's why if somebody thinks that you have actually designed a combustor based on conventional hydrocarbon fuel, say something, a burner which is designed for methane, say stoichiometric methane in a mixture which has a Lewis number of 1, and suddenly I take that burner and put hydrogen in that, because we are moving towards the hydrogen economy, and it will give you the desired performance. It's not going to happen. Okay? Because hydrogen behaves, the hydrogen flame will behave like this one. It's a considerably different behavior. In addition to that, the chemistry is significantly different. Just, it is complete digression from what we are talking about here, but I just want to make you aware of the implications. So this is the instantaneous time profile for a statistically planar flame. So if you consider this to be our x direction, y and z direction are statistically homogeneous, will actually average, and the Febvre average flame profile will look something like this. Okay. Just like a straight line. A series, C tilde profiles are a series of vertical lines. So C tilde becomes only a function of x, so we are going to show all the results as a function of C tilde. First thing to notice, you will see that as we go for smaller Lewis number, the product between the scalar flux and this one becomes positive. I showed that yesterday. If you look at this, if I now multiply see, this one has to be negative according to gradient hypothesis. Clear? If it is not negative, that effectively means it has to be counter gradient. So case A, where you had small turbulence intensity, tau SL dominates over U prime. See what happens? This red line is the zero line, positive value. Clear? Counter gradient transport. This one, big, this is release number 0.34. I told the reaction rate effects are stronger in that case. That means heat release effects are stronger. Thus, significant counter gradient transport. Follows the logic? What we talked about earlier. Next one. This one is Lewis number 0.6. Showing counter gradient transport, but the strength has come down. This one is Lewis number 0.8. Lewis number 0.6 is showing counter gradient transport, but see, it starts as a negative. Towards the unburned gas side, where the heat release effects are not strong, then it basically U prime effects are dominating. Starts as a gradient transport. As it comes towards the reaction zone, heat release effects become strong. It actually goes through a transition, becomes counter gradient. Okay? Clear? Case F. Now it shows fully gradient type of transport because tau SL is smaller than U prime. We are talking about U prime over SL 7.5 here, and tau value is 4.5. Okay? Now, next you are going to see case G, Lewis number 1.2. I told it has a stabilizing effect. The heat release effects are weaker, more gradient behavior. Okay? Now, another thing. Case B. All of these cases, case C onwards, all of them had heat release parameter of 4.5 from the table. This one has a tau value of 3, so that means heat release rate strength is lower. The velocity jump is not really heat release rate strength, it is basically the extent of velocity jump because of thermal expansion is relatively weaker in that place. So turbulence actually dominates more easily, and you are seeing significant amount of gradient type of transport. So whatever we talked about, you can see the evidence from direct numerical simulation. I told if you have the slip velocity to be positive, you will get counter gradient behavior. If slip velocity is negative, you will see gradient behavior. Exactly the same. Case C, very high positive value. That is followed by, so this is Lewis number 0.34, this is Lewis number 0.6. This one is case A, which is low turbulence intensity case. You can see is this one, which is almost equal to 0, but that's the Lewis number 0.8 case. Now Lewis number 1, 1.2, and this is the case where the heat release parameter was 3. So all the cases we saw were showing gradient type of transport that have negative slip velocity. All the cases which were showing counter gradient transport are showing positive slip velocity. Just to demonstrate, this is how the PDF of C looks like, and this is how the variances look like of these cases. This is C tilde times 1 minus C tilde, and this is the case which had a Dampoler number 6.87. And you can see it's still not equal to, but close enough. These cases have Dampoler number of the order of 0.3. Clear? So all the things that we have mentioned so far, we are showing the evidence of that based on direct numerical simulation. Fine? Effectively, all the things that I mentioned, you can see del C tilde del X is positive. So you, according to gradient hypothesis, you are going to expect negative value, but we are going to get positive value of the scalar flux where you have the counter gradient behavior. Okay? And you can see the counter gradient behavior strengthens with decreasing Lewis number. Until 2009, this was not known. Essentially, we are the first people to actually come up with this kind of discovery that essentially Lewis number, even if we put the same unbound gas turbulence, can affect the scalar flux. Lewis number, by the way, is a material property. So material property essentially in turn is affecting the behavior of turbulent scalar transfer.
That's the reason you were saying if you put hydrogen, it will behave differently.
Exactly. In the unbound gas turbulence is exactly the same for all of these cases. So flame towards in the unbound gas side is seeing exactly the same turbulence. But what happens within the flame is drastically different, as you can see. Physical significance, as I said, stoichiometric methane air. You put hydrogen blending, 20% hydrogen with methane. Methane is a good representation of the natural gas. Here you have about 40% hydrogen by volume mixed with methane. This is hydrogen air flame for equivalence ratio 0.4, and this one ethylene air flame for equivalence ratio 1.2. Turbulence is exactly the same. The fuel properties are different, in other words, material properties are different. Clear? If you look at Bray number, based on the values and based on the behavior, but this is the turbulent kinetic energy behavior as a function of turbulent kinetic energy at the leading edge of the flame, that means towards the unbound gas side. You can see the behavior is completely different. This is Lewis number 0.34. This one is the high Dampoler number flame. This is the case where the heat release rate was small, and this is essentially case F. Case F is our unity Lewis number flame for heat release rate 4.5. All of them unity Lewis number. What really happens, you can see, is drastically different. Case H showed considerable amount of counter gradient behavior. That means thermal expansion effects were stronger in comparison to the turbulence. And that effectively gave rise to considerable amount of flame generated turbulence. Okay? And that's why the turbulent kinetic energy from the unbound gas side was the case. But as the heat release effects become strong, shows considerable increase before it goes down towards the bound gas side. In other cases, the thing is there, but turbulent kinetic energy decays because kinematic viscosity goes up with the increase in temperature, and that basically damps the turbulent kinetic energy. So that's the reason eventually it drops, but this increase is because of the strong thermal expansion effect. Trying to tell effectively that the mechanism which we just discussed that affects scalar flux doesn't only affect scalar flux. It affects the underlying fluid mechanics as well. It affects your turbulent kinetic energy dissipation rate, transport as well. It's not limited to that. Probably yesterday or day before yesterday, in the tutorial we did the vorticity transport equation. And in the vorticity transport equation, there was one term called baroclinic torque, which arose as a result of the misalignment of this density gradient and pressure gradient. That term plays a very, very important role if the heat release effects are strong. Okay? So effectively, the vorticity transport within the flame will get affected if the heat release as thermal expansion effects as a result of heat release is very strong. So this is the Bray number. Roughly, you can see minimum value this, maximum value this. You can clearly see when the Bray number is greater than 1 counter gradient, when Bray number is small, greater. Again, consistent with what we told based on our analytical things. Lewis number effect, same thing, the one which has the highest strength in terms of the thermal expansion, Lewis number 0.341 shows considerable increase of turbulent kinetic energy within the flame rush. Again, positive slip velocity. But if we consider the usual definition of Bray number, because here turbulent kinetic energy is the highest. So if we consider just this bit, tau SL divided by U prime, this one will show the highest U prime, right? In other words, if I consider only this part, conventional Bray number, now we will see just an opposite effect. So make it consistent, we introduced a factor for function of Lewis number. For non-empty Lewis number cases, one possibility is this one, and that more or less captures the trend which we have seen as a function of Lewis number. So this function is such that it increases with decreasing Lewis number. What happens to the pressure? It varies as this, where T is the turbulent burning velocity or turbulent flame speed times the sleep velocity. So if this is positive, this is always positive. Rho 0 is Amberg gas density, turbulent burning velocity is positive. So if this one is positive, then pressure drops within the flame. If this is negative, it will have some positive value. But again, you can see the flame which shows the highest amount of counter gradient transport shows the highest amount of pressure drop within the flame. Okay? So effectively think about it in a simplistic form. Pressure gradient appears in the momentum equation as minus dP del T del x, right? So negative pressure gradient means a positive force in the positive x direction. Now think about Newton's second law of motion, F equal to ma. You give same force to two different masses. One is heavier, one is lighter. Which one will accelerate faster? Lighter one, right? Barn gas is lighter. you are actually subjecting it to the same pressure gradient. Burned gas will move faster in comparison to the unburned gas because that's heavier. And this differential acceleration is responsible for the transfer gradient. Clear? Now, if you have understood that, then you can actually appreciate that external pressure gradient or body force will have an impact on the scalar flux behavior as well. So, as I told yesterday, this is positive G star. So body force acting in this direction. Now heavier reactants are sitting on top of lighter products. It's an unstable configuration. You know that heavier fluid cannot sit on top of a lighter fluid. That basically gives rise to natural convection, right? So all those instabilities will actually appear here. This one, this negative G star, flame is propagating in this direction. Body force is working in this direction. Now you have lighter fluid, lighter products sitting on top of heavier reactants. It's a stable stratification effect. In fact, if you want to make it turbulent, this body force effectively tries to stabilize it. Okay? So we have defined the force term in this manner. As I said, positive G star, essentially unstable stratification, and it can be shown in the hydrostatic limit. It is equivalent to adverse pressure gradient. In the case of negative G star, it is stable stratification, favorable pressure gradient. Okay? What really happens? What different values of G star? You will see the turbulence effects are going to be magnified for increasing G star. So you will see for this one, you start to see gradient type of transport towards the leading edge of the flame where the heat thermal expansion effects are not strong. But here, for the case of this, essentially you are going to see purely for all of those cases, you are going to see gradient, counter gradient type of transport. In some cases, it doesn't show a monotonic trend. The reason it doesn't show a monotonic trend, the reason is that the turbulence effects also gets dampened when you go for the stable stratification. So that much fluctuation magnitudes change as well. Okay. Obviously, as you move from small turbulence intensity to the high turbulence intensity, it becomes less sensitive to the body force because inertial forces start to dominate, and over body force, essentially you don't see much effect. G star carries as 1 upon Froude number squared. Froude number is the ratio of inertial force with body force. So you can understand what happens for higher value of G star. Clear? Effectively, if you start with this, we get got that, and then if you differentiate it, you will get this kind of things. And what I did, I actually modeled this in this manner, where this part is the slip velocity because of turbulence, and this part is because of heat release. And based on that, I came up with an expression for the term which is coming because of the heat release. I considered that this much is taking place over the flame brush thickness. That what is going to be the heat release over a length scale of the instantaneous flame. And that gave me this kind of expression. And if I put all of them together, I got an algebraic expression. Okay? This is in principle, valid for both counter gradient as well as gradient vector transport. Alpha 1 and alpha 2 are essentially model parameters to make the scaling relations to equality relations. Okay? See the behavior, and you can judge yourself. Okay? I would say it does quite a good job. So effectively for non-unity Lewis number, these flux of reaction progress variable and the non-dimensional temperature are different. You can actually relate them in terms of their respective variances as well. Was pretty well. Now the transport equation, best closure. This is the term because of turbulent transport. I know I have told several times, whenever transport, that means it does not generate or destroy, it basically redistributes. The quantity sitting here within the derivative is a strange one. It is the scalar flux of the scalar flux. Okay? Very strange. This one is the generation of scalar flux because of mean scalar gradient. This is the scalar flux generation due to mean velocity gradient. This is the effect of mean pressure gradient. You can appreciate if I write this equation on non-reacting flow, incompressible fluid. C double prime will be replaced by C prime. C prime bar is equal to 0. This term will go away completely. Clear? This is the fluctuating pressure contribution. These two are again transport terms. They don't generate or destroy. Clear? These two are called dissipation term because whenever scalar flux behaves like a counter gradient manner, these two terms try to bring it down towards the gradient side and vice versa. Okay? This is the contribution because of the chemical reaction. So if you are dealing with non-reactive flow, this term will go. Fine? These are the behavior. You probably cannot see this one. This is the mean pressure gradient term. In cyan color, it goes like this, but it will be there in your notes. You will find that this term, mean pressure gradient term, you saw earlier where we saw high extent of counter gradient transport pressure gradient magnitude was large. High positive values of T4 basically gives rise to, it promotes positive values of scalar flux. In this statistically 1D plane, positive value of scalar flux we discussed already means counter gradient transport. The terms which are in the under this line promote gradient transport. You will find T6 and T7 are negative for this, tries to bring it down, counter gradient transport. In this case, where you take predominantly gradient type of transport, T6 and T7 are positive. Basically tries to promote gradient type of transport. In all cases, this mean pressure gradient term remains a significant contributor. Okay? Modeling of this, if you follow the same procedure as I talked about, Ui double prime is Ui minus Ui tilde by definition. Uj is Uj minus Uj tilde. And then if you actually do the algebra, you have like this, plus essentially this contribution. Whatever you are seeing, which is essentially a function of this quantity, sleep velocity, if you don't have any heat release, the sleep velocity is going to be 0. right? This part originates because of the thermal expansion effect. And whatever left here, that is the basically non-reacting contribution. That's the turbulence effect. And how turbulence interacts with the flame. That's why you have the heat contributions as well. But in general, this part effectively is the non-reacting contribution. This is the Reynolds stress conditional on reactants, Reynolds stress conditional on products. Okay? So, just one thing I want to mention. This equation tells that suddenly if I come up with model which is proposed for non-reacting flow and plug it there, it may not work properly because that completely ignores the physics associated with this. This is a model, Daly and Harlow model, proposed for non-reacting flow, does not take care of the thermal expansion effect. We talked about that this contribution comes because of thermal expansion. We actually modeled this part, which is basically the turbulent contribution part, according to Daly and Harlow, and modeled this part in this manner. And let's see the effect. Solid line DNS, Daly and Harlow model gives you this. If I just look at the reacting contribution according to the BML theory, does that, and the total model effectively does a much better job in comparison to any other model. Okay? My objective is to tell you, first we did the analytical thing, find out what physics is going on, then essentially extracted the not unclosed terms from the DNS data, and then effectively tried to capture that, benchmarked the model parameters based on the agreement of the model expression with respect to the DNS data. Okay. T4 and T5, a variety of models have been proposed. There are huge number of models. I have indicated it here. Some of the models, for example, this class of models were proposed for RAN simulation of non-reacting fluid. As a result, the T4 term, which had C double prime bar and mean pressure gradient, never appeared because that term goes to 0 in the case of incompressible fluid. You will see these models don't really perform very well in the case of physics. The models which incorporate these effects are more successful. I'm not going into that, but effectively Nishiki et al. Model, Winstead and Paul's model, Domino and Press model, these three models which essentially explicitly account for that mean pressure gradient effects are more successful in capturing the DNS behavior. Okay? Bray came up with this kind of model expression. I already told T6 and T7 act as a dissipation term. So that's why the negative sign is there. Okay? Everything else is here. This one is proposed by Nishiki, but it's not really a very good model in the sense it is only valid for counter gradients. We modified Bray's model slightly in this manner to take care of the Lewis number effects. Here is the performance. I think the new one is no longer new. It was new in 2009, but does a better job than the other alternative ones. Bray also proposed this expression for E8, that's the reacting contribution. Here, this model parameter was taken to be constant. We found this model parameter depends on this number of parameters like this. The performance. Okay. So that concludes our discussion from the RAM's point of view. Now we are entering into LES. Now in LES context, it is essentially we are going to talk about principally algebraic closure, because people don't actually solve extra transport equation for scalar flux. This is the conventional subgrade flux gradient type of model. dt is the subgrade turbulent diffusivity. Effectively, if you see here, I have SCT, that's the turbulent string number, raised to the power -1. If you replace, think it without this, that's basically your Sprague-Rabinsky model. Okay? Clark's model is given by this. It can be shown analytically that you will get this expression. Wait until the tutorial to see how one can get. Richard et al. Came up with another alternative model. This model is slightly different from this one. Here, this one is called wrinkling factor, defined like this. Huawei is basically came up this kind of modeling expression. It is this part is similar to Clark's model, but in order to stabilize the code, he actually put some gradient type of things as well. Tallis and Kant came up with this. That's very, very similar to Richard's model or Vela's model, which we talked earlier. Reimer also came up with another model which is, again, not very different from Tallis and Kant's model. All the shaded parts account for gradient hypothesis. The other part is the extra term which have been introduced to take care of the thermal expansion due to heat sequence. In this case, I am taking the scalar flux in the plane normal direction. That's why the sign convention changed. Everything negative will become a gradient transport. On the positive side, gradient transport. You can see the behavior is shown for different filter width. As the filter width increases, you can see the extent of counter gradient transport increases. Okay. So the behavior in the case of LES is also filter size dependent. Keep that in mind. That aspect was not there in the context of RAMs. Product of the scalar flux and scalar gradient, now positive value counter gradient, negative value gradient transport. Once again, you can see Lewis number 0.34 times the same flake, but DNS, but we are now processing in the context of LES. The physics within the flake remains exactly the same, but analysis is different. You can see predominantly counter gradient transport. In the case of Lewis number 1, it starts with gradient, then becomes counter gradient in the region of heat. And the gradient transport is stronger in the Lewis number 1 tuples. Model predictions. Blue line is DNS data. Effectively, let's see where it is. This is Clark's model. Clark's model you will see, and Hoyle's model, they do a very good job. This one is a standard gradient hypothesis. does not capture the behavior of DNS at all. It shows completely wrong results, wrong sign as well. Doesn't even capture the qualitative trend properly. Here, some of the models are really problematic because quantitatively they are very different. That's why some multiplier I used. Same story. Early is number 0.6, 0.8. These two models, Clark's model and Huawei's model, which are related, they tend to behave much better than other models. But you will see the quality of prediction or quality of agreement, the extent of agreement with DNS data and Clark's model deteriorates with increasing filter width. Why? You will understand in the tutorial. Small hint, you can show that that model is developed based on the Taylor series expansion, and then basically truncating some terms. So Taylor series expansion is valid, and when you are truncating the terms, you are basically considering for small departure. That's why for small filter width works, a large filter width that assumption breaks the moral. Okay? Same story. For list number 1, 1.2. Qualitatively same story. If we look at the correlation coefficients, which we talked about earlier, if the model is perfect, it will give you a correlation coefficient of 1, positive 1. This one is gradient hypothesis model. Okay? C. Correlation coefficient goes negative, that means it shows the opposite trend. In fact, in practical terms, it's almost telling you, rather than using a model, don't use any model, it will give you better result. Okay? Lewis number 0.6, same thing. You will see the high values of correlation coefficients are obtained for Clark's model and Huawei's model. But as the filter size increases, correlation coefficient goes down. As I said, the quality of agreement goes down. The same story, 0.8, you can check. Okay? One, same trend. 1.2, same trend. Is interfering with this. I will just give me one moment so that we can. We already have seen this, right? Several times. So if I now carry out velocity gradient thing, we'll get this expression. If I scale it in this manner, that gives me this expression. So that's why Clark's model implicitly actually accounts for BML type of behavior. The physics that if this leap velocity is positive, I'm going to get counter gradient transport. If it is negative, I'm going to get gradient transport. And that's why Clark's model was so successful. Clear? If you consider Huawei's model, one term was identical to Clark's model, and that's why that model was also successful in capturing scalar class behavior. So, extent of counter gradient transport increases with decreasing this number. counter gradient transport strengthens with increasing filter rate. Gradient hypothesis fails to capture the behavior under many conditions. Essentially, as soon as you go to compressible flow, I think you should start questioning the efficacy of using a gradient type of model. Okay. The behavior of Clark's model and Bhowmik's model are much better in comparison to other alternative models, but they still underpredict the magnitude of the subgrid flux for when Lewis number is very much different from unity. There are scopes for improvement, and if you use dynamic modeling, there are scopes for further improvement. So we talked about the physical mechanisms which determine the statistical behavior of turbulent and subgrid scalar fluxes. One key message when you use gradient hypothesis, please be aware of the potential limitations, and please be aware it may not actually predict your scalar flux accurately. Sometimes it may actually show you just the opposite trend. External pressure gradient body forces affect the statistical behavior of scalar fluxes or subgrid scalar fluxes. A robust numerical modeling strategy should account for both gradient and counter gradient possibilities, depending upon the condition we face within your flow. We introduced different scalar flux and subgrid flux modeling strategies. With that, I'll stop. Thank you for listening. Thank you for your cooperation. Thank you for your patience for the whole time. And that basically brings it to a close.